So here we go with chapter 2 on your year 2 applied maths course, and this is all about probability. Now you learnt about a probability a little bit in year 12. What we're going to concentrate on in this chapter is conditional probability. I'll explain a bit more about that term a little later on, but before we start I want to review set notation from GCSE. Make sure that you're really happy with what it is and how it works. So set notation is things like these symbols here and this symbol here, and using symbols to represent the relationships between sets of numbers and sets of events or outcomes. So, for instance, this symbol here represents the intersection of sets A and B. Now, the intersection of sets A and B is the place where A occurs and at the same time B occurs. So that's this bit here. In contrast, this symbol represents what we call the union of A and B. And the union of A and B is, the best way to think about it is thinking about A occurring, which is this, or alternatively B occurring, which is that. So it can be either or. So in your Venn diagram, it's the space enclosed by both of the rings here. The other piece of notation that's really handy is this dash notation here, and we read that not A, colloquially, and more formally it's called the complement of A. And notice it's complement with an E here and not an I, because we're not telling it how lovely it is. And not A is everything that is outside of A. So in this case, on a Venn diagram, it's everything that's outside of the A circle. So that's this bit here, but also everything that's outside of B as well, because all of that's outside of A. So that bit represents the complement of A, not A. So let's have a look at this in an example. Example 1, we are presented with a pack of 52 playing cards, and we are given 2 events. A is the event that the card is an ace, and D is the event that the card is a diamond. Now, before we even look to answer the questions, let's draw a Venn diagram to represent this, because it's much, much easier to answer practically every probability question if you've drawn a Venn diagram. So, ace and a diamond. Now, thinking about a pack of cards then, we know that we have 4 aces in a standard pack of cards. So in this circle here, we should have altogether the number 4, but one of those aces is also the ace of diamonds. So there is one card that is both an ace and a diamond. The remaining 3 aces will go there. And if you're thinking just about the diamonds, we know there are 4 suits in our pack of cards: the diamonds, the hearts, the spades and the clubs. And there are 13 cards in each suit, because each is a quarter of 52. So one of those is the ace and the other 12 go here. Now that's not quite finished, because in our universal set I didn't mention earlier, that means everything we are considering for the purposes of this question. So our universal set is the pack of all 52 playing cards. And of course this here doesn't add up to 52. This adds up to 16. So the remaining 36 cards, which are neither aces nor diamonds, go out here. Now, I want you to be very strict about the notation you use for probability. If you're asked to find a probability, you put a capital P in front of the thing you are finding the probability of. So, the A and D is the intersection of the 2, and that's this one card here. So if you were asked to find how many cards were in A and D, we could write that like this: the number of cards that are both aces and diamonds. But to find a probability, we want to know the number of cards that are both aces and diamonds out of the total number of cards altogether, which is 52. So our probability there is 1 out of 52, and I can leave it like that. So don't confuse this lowercase n notation, which just means how many are there of this thing here, aces and diamonds, with the capital P, which means what's the probability of this thing here happening. And please do not go writing just something like A and B equals and putting a probability without having your capital P in your brackets in front of it, because we need to make sure that we communicate our mathematics clearly for everybody else who needs to read it, and so that it helps us to organise our own thoughts clearly. So next one, the probability of A or D. It could be A, or it could be D, or it could be both. So that's everything in the circles here. So in the circles here, we have got 16 cards out of a possible 52. Now, we can leave it like that. We don't need to simplify a fraction unless we are asked to. So if we particularly needed to, we could get 4/13 from it. I don't know why I did the calculator for that. I could have done that on my own, never mind. But we can leave it like this, 16 over 52. Now, the probability of not A then is everything outside of A. So that's these 12 and these 36. So that's 48 out of 52. Let's do it without a calculator this time. Divide numerator and denominator by 4, so we've got 12/13. And then finally, the probability of not A intersected with D. So not A and D. Now let's have a think about what that looks like on the Venn diagram, do a bit of shading to help us. So not A is everything outside of A, including these 12 here. D is this bit here. Whenever you see the intersection, you're interested in where this and this overlap. So outside of A and just inside D, where do they overlap? They overlap here. So that gives us 12 out of 52, which we could simplify, but we don't have to. Right, let's move on to example 2. Now in example 2, we are not given a context for our events. We're just told that the probability of A is 0.3, the probability of B is 0.4, and the probability that they both occur at the same time, their intersection, is 0.25. The first thing we're asked to do is to explain why are A and B not independent. Now, you learnt about independence last year. Independence means this. If two events are independent, so let's put it like this. If A and B are independent, then we have an equality that holds true. We know that the probability of both of them happening at the same time is equal to the probability of one multiplied by the probability of the other. If that is true, then they are independent. Now, if we're asked to show that these two aren't independent, we therefore need to show that this is not true for these events. So let's go about it then. The probability of A in this case is 0.3, B 0.4, but that is equal to 0.12. That's not 0.25. So this product here is not equal to the probability of the intersection, therefore they are not independent. Now if we've shown that that's the case, we just need to make sure we can put a little conclusion. So therefore they are not independent. Just remind yourself what independent means. If two events are independent, it means that this one happening has no effect on this one happening. So this one can go ahead, this one can go ahead, and they don't affect each other. They don't change the chances of each other happening. So a good example of two independent events would be if I had a dice that I rolled and a pack of cards, and I took a card, taking, let's say, a king here, and rolling a 6, they would have no bearing on each other whatsoever. because this one does not affect this one. So they would be independent. Let's look at part B. We've got to draw a Venn diagram to illustrate the events A, B, and also a new event C that we've had introduced, and the probability of C is 0.2. Now, to help us do this, we're told that A and C are mutually exclusive. That means that they can't happen at the same time. An example of two events that might be mutually exclusive are if you take a card out of a pack of cards, and the first event is that the card is a king and the second event is that the card is a queen. You can't get a card that is both a king and a queen. Those two things can't happen at the same time, so they are an example of two things that are mutually exclusive. So we're told that A and C are mutually exclusive. What does that look like on a Venn diagram? It means that they don't overlap. There is no intersection because they can't happen at the same time. Now we're also told that B and C are independent. So here's this word independent again. Now we need to use that because if they are independent, then we know that the probability of their intersection is equal to the product of their individual probabilities. So let's work that out. The probability of B was 0.4 from the first part. We're told in this new part the probability of C is 0.2. So their intersection is 0.08. So these two, B and C, do have an intersection, whereas A and C don't. So our Venn diagram could look something like this. We could have A, we know it intersects with B from the first part, so there's B, and we know that B intersects with C, but not with A. So I can't put it there because that would show it intersecting with A. I could put it here, however. So we've got A, B, and C. Let's start to fill it in. The intersection of A and B is 0.25. The intersection of B and C is 0.08. I should have drawn this a bit bigger, never mind. Now let's work out the probability of A was 0.3. So A is this circle, 0.3 minus 0.25, so that's going to be 0.05 there. Now the probability of B was 0.4, so from 0.4, I'll show you on here so you can follow a bit more clearly. 0.4, we're going to take away this 0.25, and we're going to take away this 0.08. So that leaves us with a 0.07 here. And for C, if its probability is 0.2, then to work out this bit, we're doing 0.2 minus this bit here of 0.08, because that makes up the C circle. And that gives me 0.12 here. Now, we know that the probability of everything happening in our universal set, which is A, B and C, or potentially not any of them, has to be 1. So to work out what probability goes outside here, we are going to do 1 minus each one of these here. So 0.25, 0.07, 0.08, and 0.12, and that gives us 0.43. So there's a 0.43 probability that none of these three events happen at all. Let's go on to part C. Now, this one's I like this because it's really testing whether or not we understand the set notation. So let's think about the individual parts of this. And I'm going to look first of all at this bit inside the brackets. The intersection of A and not B. So let's find that first. A is this circle here, whereas not B is outside of the B. So if I were to shade A, I would shade all of that circle, and if I were to shade not B, I would go all the way around the outside plus the little bit of A here and the little bit of C here, everything outside of B. But I'm looking for where those two overlap, where do they intersect? And that would be in this little area here with a probability of 0.05. Now, remember this union symbol means that we're interested in this thing or this thing, and it could be both. So we're interested in the one we just highlighted, but we're also interested in C. So we're also interested in that there. So what we have altogether is the 0.05 there, and this C circle, which was 0.2. So our answer to that problem is 0.25. Now you have enough information to have a go at exercise 2A. Use your highlighters to help you if you need to with your Venn diagrams, and think very carefully about the difference always between the intersection, which is where two things overlap, and the union, which could be either or, including both.